All right. Good evening to everyone or wherever you are. I'm Sumant, and I'm joined by Eduardo. We both work at Snapchat. We are currently based in LA, and today we are going to talk about how the work that we've done on improving exception throwing. So just to give a quick background of what we do, so we are both working on C++ performance-related code, specifically for augmented reality. And then just to give like a quick outline of what we are going to talk about today, we are actually going to use template magic or template instantiations to reduce code load, which is something that is counterintuitive. You usually think, hey, if I have a template, you're actually going to make instantiations and increase code load, but we are going to actually use templates to reduce code load with exceptions. The second thing which we are going to do is we are going to show how you can choose the set of types that you are passing to create your exception objects. And then third, what we are going to do is we'll improve upon perfect forwarding. So how can we improve perfect forwarding to make exception throwing even better? And just to show you guys how we look, if you ever find us on Snapchat. So these are our avatars, which we call Bitmoji, and this is our team members who also have helped quite a bit on coming up with these ideas. And then just a quick background of what we've already done and presented publicly about this. So some of these ideas come from a CPCon poster presentation which we did in 2019. So whoever was there, we actually won an award for the best poster for CPCon, and that was done by our colleagues Evgeny, Fedor, and Yuri. And some of the work there which we displayed was done by Dennis. Apart from that, we have also borrowed some ideas from Folly to like further develop the framework which we built. And then Eduardo, who's also going to be presenting, also has some ideas in his zoo libraries, which we've actually implemented for throwing exceptions. So far, this code, which we've written, already runs all over the world in production on mobile and desktop. As far as we know, we don't think anybody else has put all of these ideas together in the context of exception throwing. And just like a quick plug for Eduardo's proposals here, I think Eduardo is going to dive much deeper into these ideas during CPPCon 2020 if his proposals get accepted. So please stay tuned for that as well. All right, so let's begin by what exactly exception throwing entails. So exception throwing can be broken down into these like 5 distinct steps. So the first step is we'll allocate some space for an exception object in some special section of memory. The second is to actually construct an exception object. The third would be to bring in the type info so that when the exception is thrown, the catch blocks can actually look at the type info and filter. The fourth one is to then get the address of the destructor so that the exception object can be destroyed after the unwinding is done. And then finally, we do stack unwinding, which in Itanium ABI would be a call to CXA throw. So let's like take a look at this in Godbolt, like in assembly, which I feel is like much easier to understand in terms of what's happening. So what we have here on the left is basically two.
Sumant, a little bit larger, please.
Sure. So yeah, what we have here on the left is 2 functions. Basically, are doing something very stupid. They take in 2 parameters, they check some condition, and then throw an exception. So let's see what the generated assembly is, and look at the fact that we are compiling with OS, so it's optimized for size. So the first function, the generated assembly, it just checks some condition. If this condition is true, it will jump to this label, and this label is what is doing the throw. So let's again look at the 5 steps. Step 1, allocate the exception object. Step 2, construct the exception object. Step 3, get the type info. Step 4, get the destructor. And then step 5 is pass all of these to your throw. So this is throwing exception from function check bool. Let's look at what check pointer is doing. Now you see that check pointer is repeating exactly the same code. And we are actually optimizing for binary size. So hey, this seems bad. Like why is this code repeated all over? This actually has some performance implications as well. Let me go back to the slides and talk about that. So why do we care about optimizing object code, right? So one of the problem is that because of exception throwing, all the code we saw is inline with the critical code. So it's going to reduce the efficiency of your instruction cache. So it's going to be worse performance. And for an app like Snapchat, our users actually care a lot about binary size. So reducing binary size is like a big goal for our app in general to increase engagement. And through the techniques that we are going to discuss, we are actually able to get like a 1.5% reduction in object code size without too much pain on the developer. So I think this is like a really good development for us. And to top it all, I think these techniques are more broadly applicable too. So we have many more savings to unlock. Okay, so let's now jump into what we actually did. Okay, so step one. Step one is actually just setting yourself up for success. So how do you change your code so that you have set yourself up for success? So this is what you do. So instead of calling throw directly from your functions, you create this new function called throw exception. And wherever you are calling throw, you just call this throw exception function. And let me now walk you through what this function is exactly doing. So first of all, notice that it's templated on the type of the exception object, and then it also takes a variadic number of arguments for constructing this exception object. Part two is that it's marked as no return. So we are strongly telling the compiler that this function is not going to return, it's going to throw. The third part is we are all marking it as inline. So basically, this is not changing the functionality of throw at all. The generated binary is going to be exactly the same. It's just that you have now created this new function where you can put all your optimizations into. And then step four is optional. So you can see that we have made sure that the exception is a base of std exception. You can add more conditions here. So basically, this allows you to create a single place where you can put constraints in your code. And overall, we believe that this will help help you write better code for throwing exceptions. All right, so now we have done step one. We have done the due diligence. All our code calls this separate function. And now we are ready to optimize. So let's get into step two. So step two is going to be, we are going to split our exception throwing. So this is what we do. So now let's focus on the bottom part first. So the bottom part is throw exception as before. Nothing has changed there. All we are doing is we are calling another function, which is the backend. And that backend is doing something cool. So let's look at what backend is doing. So that's on the top. So now you can see the backend is again taking templated on the type of the exception and the arguments that are needed to construct the exception. One thing that you'll notice is different. This is that this backend is marked as no inline. So basically now what we are telling the compiler is that, hey, this backend should not be inline. Every function that is calling this backend, it should make an explicit call to this backend. So now we are sort of reducing the duplication. If you remember from before, the duplication that we had, we are trying to address that issue here. And then the backend is just doing the same throw as usual. It's constructing the exception object and calling throw. So now let's look at what happens when we actually use this backend mechanism. Okay, so we have these same functions here as before, but now we...
Sorry, Sumant, again, a little larger.
So we have the same functions as before, but now we've also added the extra backend as we discussed. Now let's see what the generated assembly is. So our check bool condition, it does the same thing, check some condition, goes to this block. And now you can see that it's calling this backend function. So there's no more inlining of exception throwing into the function. Let's look at check pointer. You can see it's doing the same thing. It's again calling this backend function. And our backend is now doing the throw. So great. So we've avoided code repetition. We have removed exception throwing functionality from critical sections of our code. So great. We are doing really well. Okay, so let's see what happens next. Maybe tomorrow someone comes in and says this. Might have failed bad. Let's look at what happens now. Okay, so this function is calling the backend. The check pointer is also calling the backend. But you can now see that on line 19 and line 34, we have two instantiations of the backend. Now, why did this happen? The issue, the reason why this happened is because of, you can look at the type of the backend here. So the type of the backend in one case is a character array of size 15. And in the second case, the type is a character array of size 19. So even though it's exactly the same code that's throwing the exceptions, just because the template instantiations, you were using different types, we ended up bloating our binary for no reason. Okay, so this is something bad. We need to fix this as well. So now I would like to invite Eduardo to talk about how we go ahead and improve this.
All right. So what we're going to do is think about it for a moment. Okay, we don't really care for the purposes of the backends whether the exception object is going to be created with an array of 14 characters or 19, or is going to come from a standard string object, etc. Right? All of those things are really not that relevant. There are small differences, but we don't really care. So could we make it so that instead of having one instantiation for each possible type of exception object argument, instead of one instantiation for type, to combine many different types into a single one, and in that way funnel the number of instantiations that we're going to be doing into a single one. Of course that we can do that. So what we're going to be doing is to project from a family of types into one representative. One of those examples would be character arrays of different sizes are always going to go to just a character pointer. The same thing we can do with a string view. The same reasoning that we apply for a string text information, we can also apply to integers. We can make the distinction of whether they are signed or unsigned and things of the sort. We have an example for that. Sumant, thank you. I'll open the code. And let us first maximize the part of the code so that people can see the code better. All right. So if we go to the bottom to the throw exception, you're going to see that instead of calling the line 81, instead of calling just the backend, we're going to also be calling an intermediary, which is make throw argument, because we potentially are going to be making a conversion there, right? So that's the key. Rather than just forwarding the argument that we received to creating the exception or object in the backend, we're going to intercept that and decide whether we want to convert it or not. So, Matt, could you please show me what are the overloads for make throw argument? Down. Yes. So we have there two overloads for make throw argument, and they are distinguished using the technique of metaprogramming of Sphinx. Substitution is not a failure. Substitution error is not a failure. Whether we have a type trait that is projected for throwing, thank you, or not. So if it is not projected, we just forward it. And if it is projected, then we're going to call the projection function, and whatever we're going to return is what the projection function returns. Because I think it is important to see the metaprogramming technique. Sumant, please show me the type trait for down, please. Okay. A little bit down. There, excellent. So we have in the line 48 the trait for whether we're going to be projecting or not. And what we're doing is to use a decal type of calling an implementation function called isProjected on a value of the given argument, okay? So what we're going to be doing is to use the mechanism of overload resolution as a pattern matching engine to relieve us from work. I'm going to explain to you momentarily what I mean. Sumant, a little bit up. So then you can see the declarations of isProjected. By the way, we only need the declarations. We don't need the definitions, because all we care is the decal type of what they return, right? They are going to return false type as in line 24, which is the catch-all, or true type instead of we wanted to actually do the conversion. But for example, the line number 30, okay? The line number 30 is capturing not just a constant all value reference to a standard string, but it's also capturing the R value reference to a string and also the const R value reference to a string. So we are killing three birds with the same stone. And that's highly desirable. So that's why we use the mechanism of overload resolution as a pattern matching engine. I think that is please line 40, just show the line 40, the code.
Yeah.
And Sumant, you can explain the assembler. Just maximize the assembler so that it is easier for us to read what's happening.
Yeah, just to quickly add here, what we see is that we have projections for different types of character array and strings. Both are being projected to const char stars. And then let's go and look at the assembly that gets generated. So what you see here was, like previously you had this check bool condition and it was calling backend, but the backend back then was templated on a character array of some fixed length. But now you can see that it's now only templated on a char pointer. The same again for check pointer function. And if you see, there's only just one instantiation of our backend now for a character pointer. And that's it. So we have essentially reduced code load by removing this extra instantiation just because we were passing a character array of a different length.
Yeah, and now the next thing is to notice that we are actually not passing a character array. What we are actually passing is a reference to a character pointer. And that's another inefficiency, which is in the concept of perfect forwarding in C++. Perfect forwarding is when your function, the one that you're writing, receives arguments, you want to pass exactly the same types, the value categories to the function that you're going to be using internally, right? So if you receive something that is an R value, you want to give an R value to the functions that you're calling so that they can do whatever they want with the argument. So that's forwarding. And the concept of perfect forwarding is that it preserves the value category. But it has one deficiency that is nagging from the performance point of view, which is it converts trivial types like an integer or a pointer into references. And to convert them into a reference, they first need to be copied to the stack so that they have a position in memory, so that the calling convention can use that address instead of the value itself. So that's an inefficiency. So we had to improve a tiny bit upon perfect forwarding. That's why I call it better than perfect forwarding, which is to pass trivial types by value. And what we need to do is exactly the same mechanism. You can go back to the presentation, Sumant. Exactly the same mechanism that we used to determine whether to funnel different types into a single one. We can also detect whether the type is not converted and it is trivial. And for that purpose, you can pass it by value. Okay, let's go to that link. And this link is very simple. Scroll down so that people can see what I am converting. So notice that the argument is an integer. I'm just throwing throw exception my error on 1, 2, 3, 4, 5. So it's just an integer. But if you see in the assembler, it is calling a backend instantiated with a long argument, okay? Why? Because I think that long is the natural representative for integer, short, signed integral types in general. So that's what we're doing there. And if you see, now we don't have any inefficiency of having to put it on the stack. We are just passing it by register as opposed to a value on the stack. And let me show you momentarily in the source code the technique that we're using. We have in the source code, we have a technique to detect the case of pass by value. We have a type trait, and the pass by value is a complicated condition, but it is metaprogramming that it is not different to more complicated things that we do on a regular basis. Well, combining these four techniques, by the way, we have given Phil Nash the document that explains these things in a readable form. You don't need the slides. The links are going to be there, so you can study them at your own pace afterward. We just wanted to introduce the ideas. But what I was going to say is that doing these things, we get savings of 1.5% binary size, object code size. So we have achieved the what we set out to do. Now, I wanted to talk to you about different choices because other engineering groups, such as our colleagues at Facebook, they have arrived to different combinations of techniques. Please open the link to Facebook's Folly at the top. Thank you. We need that larger, Sumant, please. So all of the implementations of throw exception boil down to the line that you see in line 36 in this link. So what is it that is happening? The Facebook Folly code focuses on factoring out the instantiation of multiple ways of constructing an exception type And once they have solved the issue of the exception type and building that exception object, they throw it, okay? So you can see that the other throw functions are front ends to build the exception object. So that's what they make the emphasis on. But there is a problem, and we have measured that their technique is detrimental, is a pessimization in our environment, probably because we have already optimized beyond what they can, what we could achieve with just this technique. And this technique has two penalties. The number one penalty is that the only thing in the language that has access to the memory, the special memory for the exception object, is the throw primitive itself, okay? So you cannot factor the construction of the actual exception object out. It has got to be a throw. Furthermore, so if you factor out the exception object, then you had to create it and move it to the special memory. So you had the penalty of moving it. But you're also creating a temporary, and that temporary needs to be destroyed. And calling the destructor of an exception object tends not to be a no-op, for the very simple reason that the exception objects tend to inherit from classes. They have virtual destructors and therefore are overrides. So it has got to be an indirect jump, okay? Probably an indirect jump that does nothing else, but, well, it is an indirect jump. So you're introducing two penalties and a performance one that I don't like at all. So we have measured that it just sets us back. It is a pessimization from our point of view. But you can experiment. You don't have to take our view of these or our exact combinations as an act of faith. We're just telling you the techniques, and you combine them in the way that you please. I was just trying to show that there are other ways of doing this. Next slide. And we have reached the end of the presentation because we have seen how we can use templates that are notorious for introducing code bloat. We use templates to accomplish the opposite. We do judo with them. We reduce binary size by funneling different types into a single instantiation. We also showed you how you can design APIs that reduce object code by using representative types. You can also have seen how to do better than perfect forwarding by forwarding trivial values as values. And the combination of the techniques are a comparison with others, okay?
Right, that's it from our end.
Well, thank you, Ed and Sumant, for an exceptional talk. I just wanted to throw that in there. As you know, I have opinions on exceptions as well, but it's good to see somebody actually looking into optimizing this stuff, especially at compile time. So thank you for that, and thank you for the low-level details. You do actually have some questions that have come up in the Q&A. Now people have discovered that. I don't know if you can see them there. Do you still have the Remo Q&A?
I have the Remo, yes.
So on the right-hand side,
chat,
where you have the chat window, there's a Q&A tab.
Yeah.
So you can see the top voted one at the top from Dennis. Do you want to read that, or I can read them out to you?
If Const Expert covers that Svine use case, much nicer for my money. Mr. Dennis, you might be right, but I think that because we're using overload resolution, I am not sure that we can turn this into Const Experts, okay? But thank you for the suggestion. We might see if that makes an improvement. Herb Sodel claimed some time back that there is no real usage for different exception types. Well, I disagree vehemently with that, and maybe in blog postings and presentations over the coming months, I'm going to have opportunities to articulate that disagreement. Is there a reason you care to support multiple different exception types? Thank you for the question. Yes, the most important one is that in the case of a single type for exceptions, you are trying to describe the universe of potential errors, which is huge and unpredictable and very, very hard. It is a is the realm of the unknown, the things that can fail. So you need very powerful descriptive mechanisms to describe what is it that happened if you want your code to do anything other than logging and aborting. And I am a firm persuaded person on the principle that you can deal with errors. You just need to make it so that the description is actionable by programming code. And that's why you need a very rich exception hierarchy types. You might also need boosting the mechanisms to describe exceptions with other tools, such as, for example, type erasure. And I think one of my assignments at work currently is to do exactly that. So I'm going to be able to probably show you the results of the work and as well as the ideas. Okay. Another question. Have you tried using attribute called in addition to no inline? Theoretically, it should cause the throwing code to be even farther from the success path code. Thank you for the suggestion. The answer is no, but we can totally try.
Regarding the exception types, multiple different exception types, just if I may, I think that misses some of the nuance of what Herb was actually saying originally. He wasn't saying that it's of no use. He was just saying that we rarely actually use that opportunity. If you do, then obviously that's valuable, and in your case, that's clearly the case. But for most of us,
because sorry to interrupt, Phil. To Dennis's second question, the real thing here is that using exceptions as an error code gets you into a corner in which there's little that you can do other than logging and aborting. And that is the reality, that most people can only deal with errors as logging and aborting. But I think that C++ it's actually very powerful in the way that it can react to exceptions. And unfortunately, our community has not fully tapped into the possibilities to handle error.
Well, I think this is an excellent topic to pick up in the after chat. So I'm going to thank you both for now. And I'll drop you out the stream, but I hope to see you in the Remo chat rooms. So thank you both.